The Nikkei, 3rd of January, 2026. A sense of crisis in fintech. Down here. Indeed. I am Satoshi Nakamoto. As you can see, I'm a Japanese man wearing traditional Japanese garb. I've also got further proof. As you can see, I am in Tokyo. Don't mind that buffoon, Dr. Craig Stephen Wright. He's not even allowed to call himself Satoshi anymore. So, ha! Anyway, this video series is titled The Past, Present and Future of the Blockchain. Episode 1, Restoring Bitcoin, or Unfucking the Blockchain. Some mistakes were made in the original implementation, the most important, or infamous, being the true return bug, known as 0-day in computer security terms. It allowed anybody to steal everybody else's Bitcoin. We will discuss that and the hasty patch that was rolled out to fix it. Having said that, other grubby people also added stupid things and restricted the protocol in various ways, hence the necessity to unfuck it. We will discuss the Genesis upgrade, which has already occurred in February 2020, and I'll talk about the important upcoming Chronicles retrograde, as I like to call it, as it merely restores the power and full feature set of the protocol from 2009. Episode 2 is titled Awakening Bitcoin, and we will lead into that and its central innovation, namely N-Chain's push transaction technique, which improved the programmability of the protocol upon its release in April 2021. Finally, in episode 3, titled Unleashing Bitcoin, I will outline how we extend upon the push transaction building block and introduce the new layer 1 token protocol called Bolt, and how it will turn this radical Turing tape effective time machine into an active virtual machine. But in order to understand the blockchain, we must first go over some computing basics. A bit stands for binary digit. Did you know that? I didn't know that. It's a binary number with only two representative symbols, either a 0 or a 1, false or true, respectively. A number to the base of 2. In comparison, decimal is to the base 10, 0 to 9, the global standard for number representation, whereas hexadecimal, alphanumeric to the base 16, inclusive 0 to 9 and 8 F, with A being 10, F being 15, 0 to 9 being themselves 16 total symbols, the earliest global standard for computer data representation. Now, a byte is 8 bits, representing some number between 0 and 255. 256 total. You got that? Okay. A byte is the basic unit of data. We've got megabytes, gigabytes, terabytes, petabytes, zettabytes, exabytes, etc. As an aside, half a byte is called a nibble, amusingly. Now, we're not going to talk about blocks, because frankly, they're pretty fucking boring. They contain transactions, and they occur roughly every 10 minutes. That's all you need to know, for now. Actually, for the rest of the series, because we're not going to cover them at all. This, however, is a Bitcoin transaction, or TX for short, and its structure in data blobs of various sizes. TX contain a number of inputs, TX ins, and a number of outputs, TX outs. TX ins and TX outs are slightly different from each other, but also similar in some ways. They both contain one computer program each, and the programs can be of varying size or length. We call these programs scripts for short. TX outs are simpler than TX ins. They contain an 8-byte length encoded number value of how much Bitcoin is stored in them, and following that value comes the locking script or program, with its variable length encoded before it, so that TX processors know how long it is. TX ins are a bit more complicated as they depend on TX outs. In order to make a Bitcoin transaction, you must have an unspent TX out, or UTXO for short. So a TX in starts with the identifying information of the previous UTXO, namely the previous transaction ID, which is 32 bytes, plus the previous output index, a number encoded in 4 bytes. Or combined, we call this the previous out point, prev-out point, which is 36 bytes. Then after those bytes come the variable length of the program and the program itself. Programs in both the TX in and TX out contain a sequence of operations or instructions operating alongside, with, and upon blobs of data. The instructions are called opcodes, and there are lots of them. They are effectively akin to the set of assembly instructions or operations that are piped into the logic gates to be processed on the semiconducting silicon computer processing units in your phones, laptops, and other electronic chips. The scripts operate forth-like in reverse Polish notation and store memory on a stack. As you can read in the top half of this diagram here, it goes up 1, up 2, up add, up 3, up equal. And 1 plus 2 does equal 3, so true is left there at the top of the stack. They also have access to a secondary stack denoted the alt stack, but data can only be pushed and pulled from it with operations limited to the items on the main stack only, for now. Because eventually, using reserved opcodes, we're going to extend the operation set in the future and possibly introduce some fancy operations like op switch stack, which would allow us to do exactly that. In the beginning, there was no blockchain. It began with its Genesis block on the 3rd of January 2009, containing a single special coin-based transaction, Bitcoin's most famous. Here's what it looks like in hex, and it contains a very famous message. Chancellor on the brink of second bailout for banks. That's exactly 17 years ago to the day of the article in the Nikkei I showed you at the start of this video. What a delta. Curiously, that article contains a list of private legacy banks, not fintech companies as we would normally know, like Stripe, PayPal and the others. So it's not fintech in crisis, it's the banks. Nothing has changed since the Genesis block nearly 2 decades ago. In any case, this is what the OG Genesis transaction looks like. The output is what's known as a pay-to-public key script. If I wanted to spend the Genesis UTXO, which I don't because I don't want it to be pruned, so it'll stay there forever, symbolically as a massive double middle finger to the money printers, I would create a transaction referencing it via prevout point and provide a signature from the Genesis private key, the counterpart of the public key it's locked to, and create a new output. But we require some further information about this, so here's a brief synopsis of some blockchain fundamentals. As we've already shown, the pay-to-pub key output in the Genesis transaction, it contains basically, for simplicity's sake, only one opcode, opchecksig. What is opchecksig? Well, it validates the elliptic curve digital signature algorithm, which are mathematical constructs for creating and validating digital signatures created over data using digital keys. The other standard output, pay-to-pub key hash, is thought of to be slightly more secure in the sense that the pub key is only revealed upon the unlocking of the UTXO, e.g. when spending it. It contains a few more opcodes. I'll talk about them shortly. Notably, it contains a hash. But what is a hash? A hash function is a data fingerprinting computation, basically fixed length output calculated from any length input. An input is read byte by byte through the algorithm. Output serves as an identifying abbreviation for the data. Input cannot be recomputed from the output. It's a one-way function. So hypothetically speaking, this is what would happen if I spent the Genesis output. The miners or block creators would combine the newly created input unlocking script, which contains a signature I would provide with the Genesis UTXO private key, and check if the signature is valid. Originally, they would concatenate the scripts together with the code separated between them and run them to check the result. But this is where a mistake was made. The 0 day I mentioned previously, and quickly patched to stop the bug. People could come along and use any output and trick the miners into unlocking them by providing a script that would exit before the code separator and the locking script altogether. That script would finish on or contain only 2 opcodes, up true, up return, e.g. exit and finish, with true being the result. Obviously that would be fixed quick sharp, so input scripts were restricted to push data only, and you couldn't run any logical opcodes in them from that point onwards. Also, the concatenated scripts were made to run one after the other rather than as one long script, with the final result always depending on the result of the second part or output script, e.g. have the UTXO locking requirements being satisfied. But anyway, what exactly must be signed in order for a signature to pass one of the checksig opcodes? It's called a sig hash preimage, and we'll discuss that in detail in the second video, but first I'll outline how we save Bitcoin in the Genesis and Chronicles releases. I was going to include a synopsis of the ECDSA algorithm, but safe to say you can think of it as a simultaneous equation whereby one person can provide an answer and keep a secret, and the other person can verify the answer without knowing the secret. Malactors put artificial limits and restrictions on the block sizes, script sizes, transaction sizes, and refused to restore the full opcode set in order to stifle the Bitcoin blockchain from growing to surpass the velocity, efficiency, and ability of the current financial system. But we restored it anyway. Ha ha. And here's how we did it. Notably, we have a new unbounded and simplified payment verification processing node built with microservices that's actually only restricted by the Internet Protocol version 4 itself, named Terranode. In Genesis, we restored the original functionality of op return, improved big number arithmetic capabilities, restored nlock time and end sequence to their original functionality, and removed most of the retarded limits enforced by people paid by Visa and MasterCard. Lol. And finally, in Chronicles, we are restoring a further collection of opcodes, most importantly reintroducing arbitrary processing of operations in the unlocking script. The team over at the Bitcoin Association were actually about to make a small mistake regarding op checksig in the unlocking script until I noticed, and I asked Richard Mills, the lead C++ engineer from nChain, could I speak to his boss? Which is a joke, of course, as I'm Satoshi Nakamoto, the Japanese banker. As Jim Carrey says, Ohio, konbanwa, sayonara.